seconds. The patch will expand exponentially. To make things work, you need to expand by a factor of about 10 to the 28, which takes our initial region of 10 to the minus 28 centimeters up to about 1 centimeter, which would be the size of the visible universe at the end of inflation. That takes about 100 doublings. And that would take about 10 to the minus 35 seconds, using these numbers typical of grand unified theories. There's no reason to believe that there was only that much inflation. There could have been much more, and that's also consistent with everything we see. It takes this much inflation to make the universe as big as what we see, and the universe could be much bigger, and we have no way of knowing. Now we need to end this inflation, and that happens more or less naturally because this repulsive gravity material that's driving the accelerated expansion of the universe is fundamentally unstable. So it will decay in the same sense that radioactive materials decay. It doesn't mean that they rot. It means that they convert their energy into some other form of matter. So it can decay into non-repulsive gravity material or attractive gravity material. And when that happens, it releases energy. And that energy produces particles. Those particles collide with each other and rapidly form just a hot soup of particles. And that hot soup of particles is exactly the starting point of the conventional Big Bang theory. So this is where the prequel ends and the main feature starts. This is where conventional cosmology takes over. Standard cosmology begins at this point, with inflation having served the purpose of creating the initial conditions that conventional cosmology had always assumed. Now there's one caveat here. The decay that I talked about happens almost everywhere, but not quite everywhere. And that will be important when I talk later this evening about the multiverse. The fact that we get a multiverse instead of just one universe is basically related to the fact, basically a consequence of the fact that inflation doesn't quite end everywhere. But we'll come back to that. So this is my description of how inflation works. What I want to do next is to explain why we think there's a good chance that the universe actually underwent this process called inflation. It's not merely something which the laws of physics say could happen, but there actually are some features of our universe which seem to strongly suggest that this process actually did happen in the history of our universe. So there are three things I want to talk about. Oh, I'm not there yet. Sorry, I jumped the gun. While this material is expanding, there's an important point which I forgot to make. You would think that everything would thin out as it expands. If you take an ordinary gas and expand it by a factor of 10 to the 28, there's essentially nothing left. It just becomes essentially vacuum-like. However, that's not the case for this repulsive gravity material. The repulsive gravity material actually maintains its density as it expands by this tremendous factor. And this really is what I was talking about earlier when I talked about the actual creation of matter by inflation. The density of matter is maintained through this enormous expansion. It's hard to know how that could possibly happen and still be consistent with the basic idea of conservation of energy. We're not throwing out conservation of energy here. Conservation of energy is a fundamental principle of physics. The physics community would not accept this if it actually violated the conservation of energy. So the claim is that energy actually is conserved as a fantastic amount of energy is appearing in the form of this repulsive gravity material as it expands from 10 to the minus 28 centimeters across all the way to 1 centimeter across. And in order to make that possible, we need another rather dramatic feature of the laws of physics, which is something, again, I call a miracle. This is my miracle number 2, which is essential to make inflation work. And that is that even though energy is conserved, which is what you were always told, there's a new feature that very likely you weren't told, which is that energies are not always positive. And in particular, the energy of a gravitational field is negative. So as the universe is undergoing this process of inflation, with more and more energy materializing in the form of this repulsive gravity material, at the same time, more and more negative energy is materializing in the form of the gravitational field that fills this region. So the total energy, which is the energy of the material plus the energy of gravity, has a big positive contribution and a big negative contribution. But it adds up to something that's incredibly small and is constant as this goes on, and could very well have been 0 from the start. We don't really know. But as far as we can tell, there's an essentially perfect cancellation in our universe of the energy of matter and the negative energy of gravity. So while you would expect that it would take a huge amount of energy to build a universe, in fact, we now think that it really takes possibly no energy at all to build a universe. So as I said, the positive energy of the repulsive gravity material was compensated by the negative energy of gravity, with the total energy of the universe very possibly being exactly 0. OK, now we can go on to what I was talking about prematurely a minute ago. I'd like to now describe some features of our universe which seem to strongly suggest that our universe really did undergo this process called inflation. So I want to talk about 3 of them, so you can count. That's number 1. The first is the large-scale uniformity that we see in the universe. And by that I mean a number of things, but in particular, if we look around the sky, we can measure this cosmic background radiation, 2.7 degrees or 3-degree radiation it's sometimes called, which we think of as the afterglow of the heat of the Big Bang itself. So when we look at this radiation, we're really seeing the matter immediately after the Big Bang. And the surprising thing is that it's unbelievably uniform. No matter what direction you look, you see the same thing. You can describe this energy as a temperature. And this temperature is uniform across the sky to an accuracy of about 1 part in 100,000, which is really unbelievably uniform. Now, if you have any system, there's something called the 0th law of thermodynamics, which says that if you wait long enough, it will come to a uniform temperature. So in principle, we understand how this might have happened, that everything came to the same temperature. But you can calculate how long it might take for things to come to the same temperature. And one key principle which you expect to never be violated is that nothing moves faster than the speed of light, according to the laws of physics as we understand them. When you apply that to the behavior of the early universe, you're seeing this cosmic background radiation, which we believe was formed at about 400,000 years after the Big Bang. You can calculate whether or not there was enough time for things to reach a uniform temperature by 400,000 years. And the answer is a resounding no. Within conventional cosmology, if the universe did not start out completely uniform in temperature, there's no way it could become completely uniform in temperature unless you could transfer energy and information at about 100 times the speed of light, which is strictly taboo according to all of our understanding of the laws of physics. Nothing goes faster than light. So within conventional cosmology, you either have to assume that the universe started out completely uniform, which means at least uniform to 1 part in 100,000, or there's just no way to explain how it got to be completely uniform when, as we see it in the cosmic background radiation. So one of the nice things about inflation is it gets around that problem completely. And it does it in a way that's really pretty obvious once you understand what inflation is about. Inflation inserts into this prehistory of the Big Bang this period of extremely rapid exponential expansion. And what that means is that if you trace the universe back to the time before inflation, it was vastly smaller than you ever thought it could have been in the context of conventional Big Bang physics. And during this time period before inflation, when the universe was incredibly small, 10 to the minus 28 centimeters across, there was plenty of time for it to come to a uniform temperature by exactly the same processes by which uniform temperatures are normally established by this 0th law of thermodynamics. It's the same thing that causes a hot pizza to become cool when you take it out of the oven. It's just a question of whether or not there's enough time for that to happen. But with inflation, the universe before inflation was so small that there was enough time for it to come to a uniform temperature.